Math 213 students, this is section 7.4, the singular value decomposition. This is the last section that we'll be covering in this course, and this is part 2 of the section, so if you haven't listened to the first part of the lecture, you should go back and do that now before proceeding here. We decided to split it up for a couple reasons. First, it's a pretty long section and a lot of material to digest, so we figured if we broke it up into 2 bite-sized pieces, that make it a bit may make it a bit more palatable for you. Second, kind of like the last Harry Potter book, we figured we'd make a bit more money by splitting it up into 2 pieces here. We talked about going kind of the Hobbit direction and breaking it up into a trilogy, but we just didn't feel like there was enough source material, so we'd have to put too much filler in. So this is part 2, the last part of this section, and let's dive right in. So let's give you a bit of a summary from last day. Here's the context, the setting that we're in. A is an m by n matrix. Okay, it can be any matrix. It doesn't have to be square. It doesn't have to be symmetric. It can literally be any matrix that you write down. It has m rows and n columns. Then if we take the matrix A and we multiply A transpose times A in this order, then we will always get a square matrix and it'll always be a symmetric matrix. Now, because it's a square symmetric matrix, we can go ahead and find the eigenvalues of that matrix. So lambda 1, lambda 2, all the way up to lambda n are going to be the eigenvalues. And from now on, what we're going to do is we're going to assume that our eigenvalues are listed in decreasing order. So lambda 1 is the biggest, then lambda 2, all the way down to lambda n. Now, one of the facts that we proved last class is that these eigenvalues all have to be non-negative. So they're all greater than or equal to 0. Now, that's not always going to be the case with just any random matrix you pick. There could be negative eigenvalues. But if your matrix looks like A transpose A, or you've built it in this way, then it's guaranteed that you won't get any negative eigenvalues. So that's an important thing to keep in mind. Also, because the matrix A transpose A is symmetric, when we find the eigenvectors, we can always assume that we can find orthonormal eigenvectors. So we're going to find eigenvectors v1, v2, all the way up to vn, and we can assume that these vectors are unit length, or they're all length 1, and we can also assume that they're all orthogonal to each other. Okay. Now again, that orthogonality, the fact that these eigenvectors are orthogonal to each other, really relies on the fact that our matrix A transpose A is symmetric. Okay. So we've got our eigenvalues, we've got our eigenvectors for A transpose A. Now, because our eigenvalues are all non-negative, we can take their square roots, and when we do that, we get a bunch of values which we call the singular values of our matrix A. All right. So again, we think of the eigenvalues as being the eigenvalues of A transpose A, but we think of their square roots as being the singular values of the matrix A. Okay. So these singular values are things that we think of them as belonging to the matrix A, or they tell us something about the matrix A. Well, given a matrix A, we can always split it up into 3 pieces like this: U times sigma times V transpose. And each of these pieces sort of has special properties that we'll describe here. Okay. So the first is that sigma, the matrix that goes in the middle, is one of these sort of diagonal matrices. Now I put diagonal in quotes here because it's not an honest diagonal matrix. It's not a square matrix, but it's a matrix that's going to be the same size as the matrix A. And what we do is we put the singular values, sigma 1, sigma 2, and so on, down the diagonal part of the matrix. Starting in the top left corner, we go down the diagonal, plugging in our singular values. So that's how we find the matrix sigma. The matrix V is an n by n orthogonal matrix whose columns are the eigenvectors v1, v2, all the way up to vn. Okay? So remember, an orthogonal matrix is a square matrix with orthonormal columns, and the columns of this matrix V are just these orthonormal eigenvectors that we found earlier. Okay, so that tells us how to find the sigma and the V part of our decomposition here. How do we find the U part? Okay, well, the U part is not too bad usually. U is going to be an m by m orthogonal matrix. So again, it's going to be a square matrix with orthonormal columns. And the way we compute these columns is we take the V vectors that we found in the previous step, we multiply them by the matrix A, and then we divide by the corresponding singular value. Now that's going to give you a matrix that's of unit length, and that's going to give you a vector of unit length, and that vector will be one of the columns of the U matrix. Okay, Now you run into a bit of a problem here sometimes, okay? Because the matrix V and the matrix U are not the same size necessarily. For example, V might be a 2 by 2 matrix and U might be a 3 by 3 matrix. If you take these eigenvectors here, well, if V is 2 by 2, that really means you only have 2 of them. But in order to build up the U matrix, you really need 3 U vectors. So you only have 2 V vectors to plug into this equation, and that means you're only going to get 2 U vectors using this little formula here, okay? So what you have to do in that case is you take the 2 U vectors you have, and then you have to find a third vector that's orthogonal to the 2 vectors you already have from this formula, okay? So that happens when n is smaller than m. Okay, it's like this formula that we have that gives us the U vectors doesn't give us enough vectors, so we have to go out looking for some of our own. Okay, and we'll see an example of how this works. But that's what the second line here says. It says we have to fill in extra vectors to get an orthonormal basis if necessary. Then the last fact we talked about was that hydroxychloroquine has not been proven effective at treating COVID-19. So keep that in mind as you're going through these examples here. All right, so let's do an example here. Let's find a singular value decomposition of this matrix here. So remember, what this means is we want to take the matrix A and we want to split it up into 3 pieces. U sigma times V transpose, where the matrix U, sigma, and V have the properties that I described on the previous slide. So the first step that we want to do here is we want to find the singular values of the matrix A. Okay. Now, in order to do this, we need to find the eigenvalues of A transpose A first. Okay. So we look for the eigenvalues of A transpose A. So A transpose A is equal to 1, 1, 0, 1, 0, 1 along the columns, and then times A is 1, 1, 0 is the first row, and 1, 0, 1 is the second row. So when we multiply these together, we're going to get 2, 1, 1, 1, 1, 0, and 1, 0, 1. All right? Now, a lot of you will recognize this matrix. It's one of the matrices we saw on one of the slides in the last lecture. And we actually have already found the eigenvalues of this matrix. So normally you'd have to go and find the characteristic polynomial. Then you'd have to find the roots of the characteristic polynomial. But we already did that work on one of the previous slides. So I'm just going to write down the result we found here. So this matrix has eigenvalues lambda 3 lambda 1 equals 3. Lambda 2 equals 1, and lambda 3 equals 0. Okay. Now notice we write them in descending order, so the biggest one comes first, and then we go sort of in decreasing order. And second of all, notice that each of these values is non-negative. So we didn't get any negative eigenvalues, which is what we would expect because we were studying a matrix of the form A transpose A. So to find the singular values, so this tells me that the singular values of A are just the square roots of these eigenvalues we found. So sigma 1 equals rad 3, sigma 2 equals rad 1, which is just 1, and sigma 3 equals 0. So with this information in hand, we actually have enough information to build the matrix sigma. So our next step is going to be to build sigma. And what we do to build sigma, oops, that is not a nice looking sigma. Okay. So in order to build sigma, we remember sigma is going to be the same shape as the original matrix A. So A was a 2 by 3 matrix, so sigma will also be 2 by 3. And sigma is just built by taking the singular values that we found, sigma 1, sigma 2, putting them along the diagonal, and then filling in the rest with zeros. So in this case, our matrix looks like rad 3, 1, and then 0, 0, 0, 0. Okay. So this is our sigma matrix. Now you might be kind of concerned because notice we found that we had 3 singular values. rad 3, 1, and 0. When we went to plug those singular values in, notice as we moved along the diagonal, we only had room for the first two. We didn't have room for that third one. Now that's going to happen sometimes. You're going to run out of room to put all of the singular values in. But the only singular values that you ever won't have room for will be 0 singular values. In other words, you will always have enough room in your matrix to plug in the non-zero singular values. And the reason we know that is because remember, when you start off with the matrix A, the number of non-zero singular values you get is equal to the rank of the matrix. So in this case, we found 2 non-zero singular values, and our matrix has rank 2. And so that means that we always have at least 2 rows and at least 2 columns. And so if you start plugging the singular values in, you'll always have at least enough room for the non-zero ones. Okay, so again, you may not have enough room to fit all the 0 ones in, but you always will have enough room to fit the non-zero ones in. Okay, so this is our sigma matrix. And we can, once we have our sigma matrix in hand, it's time to start looking for our V matrix and our U matrix. All right, so our next step, step 3 I think we're on, we're going to find the columns of the V matrix. Remember, these are going to be orthonormal eigenvectors of the matrix A transpose A. Okay, so we're just going to go through our list. We're going to start off with our eigenvalues, and we'll just find the corresponding eigenvector. So let's start with our lambda 1. That's equal to 3. So A transpose times A minus 3 times the identity. So again, at this stage here, this is now just a regular eigenvector computation. So we're just computing an eigenvector. This is exactly like we've done it, probably about 130 times up to this point. So I'm going to subtract 3 off the diagonal, and this is the matrix I get. And again, we're not subtracting 3 off the diagonal of the original matrix. We're looking for eigenvalues of the eigenvectors of this matrix. So that's the one we're focusing on. So we subtract 3 off the diagonal there. We get this matrix. When we row reduce, what do we get? Well, row reducing this in my head, just eyeballing this, we get 1, 0, negative 2, 0, 1, negative 1, and 0, 0, 0. Okay, and so my first row tells me that x is equal to 2z. My second row tells me that y is equal to z, and z is a free variable. Okay, so my eigenvector x, y, z, I can take x and I can replace it with 2z. I can replace y with z. And if I factor the free variable z out, just like I normally do, I get 2, 1, 1. Now, I can pick z to be anything I want, but ultimately I'm going to have to normalize this vector anyways. So I might as well pick z to be like the length, 1 over the length of that vector or something, right? Like I can pick z to be 1, and that's fine, but ultimately I'm going to have to normalize. So I think I'm going to pick z to be like 1 over rad 6. And if I pick, say, z to be 1 over rad 6, then this gives me the vector v1, which is just 2 over rad 6, 1 over rad 6, and 1 over rad 6. All right. Now again, you could have picked z to be anything, but then you'd have to normalize anyway. So you might as well, just normalize here. So we okay. So you might as well normalize, in one step if you want. But if you're not comfortable with that normalization step, then definitely break it up into 2 pieces. That's totally fine. So that's lambda 1 equals 3. Let's do lambda 2 equals 1. So this is our next eigenvalue. So we take A transpose A minus the identity. This is going to give us the matrix. Maybe I'll draw a little dividing line here just to keep us sort of on track keep things from getting too messy. So I'm going to subtract 1 off the diagonal. And I get this matrix. And when I row reduce, I get the matrix 1, 0, 0, 0, 1, 1, and 0, 0, 0. So this one here tells me that x is equal to 0, y is equal to negative z, and again z is free. So when I do my replacements here, I get 0, negative z, z, which is just z times 0, negative 1, 1. And again, I can pick z to be anything non-zero I want. I'm going to pick z in this case to be 1 over rad 2, just because that's going to give me a unit vector again. So v2 is equal to 0, negative 1 over rad 2, and 1 over rad 2. Okay. Now again, as a quick sanity check, what you can do is you can check that first of all, you can always, anytime you get an eigenvector, you can always multiply it by the original matrix, and you should see that multiplying by the original matrix is just the same thing as scaling it by the eigenvalue. So in other words, if we take the matrix A transpose A and we multiply by this vector, I should just get the result should just be 1 times this vector, or in other words, it should just be the same vector. Or I could take this vector and multiply by A transpose A, and I should just get 3 times this vector as my result. Okay, so you can always check that the vectors you're finding are indeed eigenvectors. Another sort of sanity check that you can do is, because our matrix A transpose A is symmetric, you can take the 2 eigenvectors you already found, so say v2 and v1, and if you take the dot product of these 2 eigenvectors, you should see that they are orthogonal to each other. Okay, and that's true, or that should be true, because the matrix A transpose A is symmetric. Okay. So not only can you check that they're both individually eigenvectors, you can check that they both are orthogonal to each other. And again, that is true because they come from different eigenvalues of a symmetric matrix. Okay. So we have our V2. Let's go ahead, let's draw a nice dividing line here in red. Okay. I wish I knew what color red this was. I was watching it was like a couple weeks ago. I turned on Bob Ross on Sunday, and that man is a master. If you've never watched Bob Ross, it is the most soothing, relaxing experience of your life. And he has such. I mean, they're the real names of the colors, right? Like phthalo blue or whatever, and like he named all the colors are like the real color names. And so I wish I knew what color of red this was, and I could try and emulate Bob Ross a little bit, but. It's red, and then the other color I have here is blue. And I can use green if you want, but yeah. Sorry, I don't have more descriptive names for those. All right, so lambda 3 equals 0. So we're going to do A transpose A minus 0 times the identity. That's going to give us the matrix, just the original matrix, 2, 1, 1, 1, 1, 0, and 1, 0, 1. And we row reduce just like normal. We get the matrix 1, 0, 1, 0, 1, negative 1, and 0, 0, 0. So this first line tells me that x is equal to minus z, y is equal to z, and our z is the perennial free variable there. Okay, so we take our vector x, y, z, our eigenvector, we make the replacements that we can make, so we get negative z up here, z here, and then z here. So we get negative 1, 1, 1 when we pull the z out. And again, if I want to kind of normalize, I might as well take z to be equal to, say, 1 over rad 3. I think will do it for us. So that tells me that my v3 vector is negative 1 over rad 3, 1 over rad 3, and 1 over rad 3. And I'm running dangerously close to being out of room on the bottom there. So hopefully you can read that. That vector again is negative 1 over rad 3, 1 over rad 3, and 1 over rad 3. So with these three vectors, we can again check that they're all orthogonal, which they should be because the matrix A transpose A is symmetric, and these three vectors are eigenvectors from different eigenvalues. So they're all orthogonal to each other, they're all eigenvectors, and so we can go ahead and we can actually build our V matrix using these three vectors. So my V matrix is going to be 2 over rad 6, 1 over rad 6, 1 over rad 6. Can you guys hear that? That is my daughter practicing her piano. I normally make these videos late at night, but it's not late at night right now, so she's practicing piano. Hopefully it adds a little bit of ambiance, a little bit of sort of serenity and just a nice sort of atmosphere to this video. Maybe you can't hear it, and maybe it sounds like I'm just making things up. All right, so we have our matrix V here. Now, V is an orthogonal matrix, so meaning it has orthonormal columns. And again, a quick way to check this is you could take, say, V transpose times V, and you should get the identity. Okay, so that's another thing you can check just to make sure you're kind of doing things the correct way, or in other words, that you haven't made any mistakes. So up to this point, we found our sigma matrix, we found our V matrix. The only thing left to do is find our U matrix. Okay, so that'll be the final step in this process here. I don't know what step we're on. I'm going to guess we're on step 4. Okay, so we want to find the columns of the matrix U. Okay, now remember, in order to do this, we actually have a formula that works most of the time. Okay, and the formula tells me that the vector U is equal to 1 over sigma I, or sigma 1, times AV1. Okay, so in other words, it's 1 over our first singular value, which is rad 3, times the matrix A, which is 1, 1, 0, 1, 0, 1, times the vector V1 that we found. That's 2 over rad 6, 1 over rad 6, and 1 over rad 6. So when we multiply these, 1 over rad 3. So this gives me 2 over rad 6 plus 1 over rad 6 plus 0. So that's 3 over rad 6. And then downstairs we get 3 over rad 6 again. Okay. Now if I multiply in the 1 over rad 3, I'm going to get rad 3 over rad 6, which is the same thing as 1 over rad 2. Okay. So the nice thing about this formula is, first of all, you're going to get a vector of the correct size. So V is a 3 by 3 matrix, but U is going to need to be a 2 by 2 matrix. And you can kind of see that the size works out in our favor right here. The other nice thing that's going to happen is that the components of this, or the vector that you find here, it will automatically be a unit vector. So that's kind of nice. And actually, we proved that fact. We proved that fact earlier in the last class. Remember, we proved that the length of AVJ is just equal to the square root of lambda j, which is just sigma j. So the length of this vector right here is just equal to the singular value sigma 1. And so by dividing by by multiplying by 1 over sigma 1, we're really just kind of normalizing right here. So we automatically get a unit vector, which is a nice feature. And then so for U2, it's the same thing, 1 over sigma 2 times AV2, which is 1 over 1, 1, 1, 0, 1, 0, 1, times our V2 vector, Okay, so when we multiply these, we get negative 1 over rad 2 and 1 over rad 2. Okay. And again, we find that we get a unit vector. Now, another fact that we should notice is that this vector we found here should be orthogonal to this vector. Okay, and again, this came from that big proof that we showed last class that the vectors AV1 all the way up to AVR, where R is the rank of the matrix, we proved that these vectors were an orthogonal basis for the column space. And in particular, that means that these two vectors, this vector AV1 and this vector AV2, have to be orthogonal to each other. Okay, so we found these two columns here, and it turns out that U is just going to be a 2 by 2 matrix, and so that's all we need. So U is just equal to 1 over rad 2, 1 over rad 2, negative 1 over rad 2, and 1 over rad 2. Okay. Now, one thing to keep in mind here is the order that we do everything in is now kind of important. When we did diagonalization, you were kind of allowed to swap the eigenvectors around if you sort of swapped the singular values around. Here, we're always going to assume that our singular values go from biggest to smallest. And when we write down the vectors in the matrix V or the vectors in the matrix U, we still are going to respect that order. So the eigenvector that comes from lambda 1 is equal to 3, that's going to go first. Then lambda 2 is equal to 1, then lambda 3 is equal to 0. So the eigenvalue of 3, 1, and 0 go in that order. And then, we took these vectors and we used them to find U1 and U2, and we sort of keep going with that order as we write everything down. Okay, so we've basically done everything now. We figured out our sigma matrix, we found our V matrix, and we found our U matrix. The only thing left to do is to just check our work, make sure we didn't make any algebra mistakes along the way. There's plenty of opportunities to make algebra mistakes, so it's always a good idea to check our work. So what we should do is we should take the matrix U, we should multiply it by sigma, and then we should take V transpose. Okay, so the matrix we found up here was the matrix V. When we plug it into the formula, we want to plug it in as a transpose. And if you multiply those matrices out, you should get the original matrix back. So here's what that should look like. We have our U matrix, our sigma matrix, and our V transpose matrix here. And if we do that multiplication, we see that we do indeed get the original matrix back. So well done. Let's pat ourselves on the back. Might be time for a quick water break or just celebratory. Go get a snack or something like that. Open up a bag of Cheetos or whatever snacks you have around, because we've done a lot of work. It's definitely a long process to kind of do one of these examples. Now, we will do another example right now where instead of a 2 by 3 matrix, we'll do a 3 by 2, and things work out a little bit different there. So it will be important to kind of see a few more examples just to make sure we can kind of handle everything. But these are the basic components that we need to do. So riding high off the success of this last example, let's see another one. So let's find the singular value decomposition of this matrix here. So just like in the previous example, we're going to start off by trying to find the singular values of the matrix A. And in order to do that, we need to find the eigenvalues of A transpose A. So we're going to find the eigenvalues of A transpose A. So, A transpose A will be 1, negative rad 2, 1, negative 1, negative rad 2, and negative 1 times A is 1, negative rad 2, and 1, negative 1, negative rad 2, and negative 1. All right? So when we multiply these together, we are going to see we're going to get 1 plus 2 plus 1 is 4. Then we're going to get 0 here, and we'll get a 0 here, and last of all, we will get a 4 here. All right? So our matrix ends up being a diagonal matrix, which is really fortunate for us. We don't have to find a characteristic polynomial. We don't have to do much work, because for a diagonal matrix, the eigenvalues are just the values that are on the diagonal. So in this case, the eigenvalues are 4 and 4. Okay, so they're just the values that are on the diagonal. Now remember, that's true for any upper triangular matrix, any lower triangular matrix, or any diagonal matrix. The eigenvalues are just the things that show up on the diagonal in those cases. All right, so that was a nice turn of events. It turned out that we didn't have to do much to compute the eigenvalues. So this tells us then that our singular values of A are just sigma 1 is rad 4, which is 2, and sigma 2 is rad 4, which is 2. Okay, so that allows us to build our sigma matrix. Now remember, our sigma matrix should be the same size, the same shape as the original matrix A. So it's going to be a 3 by 2 matrix. And we start off by putting our singular values just here along the diagonal, and then filling in the rest of it with zeros. Now in this case, we had room for both of them, which is good. And again, remember, you'll always have room for the non-zero ones. So we can fill up our sigma matrix like that. Okay, and we're done that first step of this problem. The next step again is to figure out what the columns of the matrix V are going to be. So what we want to do is we want to find the eigenvectors of this matrix here. Okay. All right, so we're going to find the columns of V. In other words, we're going to find the eigenvectors of A transpose A. Okay, so in this case, we only had one eigenvalue show up, and it showed up with multiplicity 2. So lambda 1 equals lambda 2 equals 4. So we're going to take A transpose A. We're going to subtract 4 times the identity. Now remember, A transpose A was just this diagonal matrix here with 4 on the diagonal in both spots. So when we subtract 4 times the identity, it is easy to see that we're just going to get the 0 matrix. 0, 0, 0, 0. Okay. Now I don't know that I don't know that we've seen an example that works out quite like this. So you get it down to the 0 matrix, and there's no row reducing left to do, and but it's kind of confusing because we're used to seeing matrices with leading variables with pivots and things like that. So if our matrix has no pivots, we might have to stop and just kind of make sure we're kind of understand what's going on here. So since our matrix has no pivots, that means that every variable is a free variable. So x is free and y is free. Okay, and so that means if our eigenvector is xy, well, we don't have any equations to replace either of these variables. So they just have to kind of stay put. They're both free variables, so we're not really going to be able to get rid of them. But what we do is we just split up our vector like we normally would. So this becomes x times 1, 0 plus y times 0, 1. And this gives us two eigenvectors of v1 equals 1, 0 and v2 equals 0, 1. Okay. Now, it's worth stepping back for a minute and just reminding ourselves that we want the two eigenvectors we find to be orthonormal. Okay, so we want them to be orthogonal to each other, and we want them to have unit length. Now, because these are two eigenvectors from the same eigenvalue, it's not guaranteed that they're going to be orthogonal to each other. If they had come from different eigenvalues of a symmetric matrix, then we would know that they have to be orthogonal to each other. But because they came from the same eigenvalue, it's actually not guaranteed that they will be. But if we check, we can actually see that we got lucky in this case, and they are in fact orthogonal to each other. So we don't have to do Gram-Schmidt. We don't have to make them orthogonal. They're just fortunately they're already orthogonal, and so that's really good news for us. The other piece of good news is that they're already unit vectors, so there's not even any normalizing we have to do. But we really kind of hit the jackpot with these vectors here. We really hit the jackpot with this problem because it was turning out to work out really nicely. So this tells us then that our V matrix is just 1, 0 and 0, 1. Okay, so we take these two vectors and we plug them in as the columns of our V matrix. And so that that does, so now we've got our sigma matrix, we've got our V matrix. Let's kind of separate our work here. I'm going to use a nice sap green before going back to work with this beautiful Prussian blue I have here. So the final step is to find the columns of the matrix U. Okay, now remember to do this, we have this formula. So our first column, U1, is going to be 1 over sigma 1 times AV1. Okay, so this is 1 over 2. That's our first singular value. Our matrix A is 1, negative 1. Pair of negative rad 2's in the middle. And then a 1, negative 1 here. And our V1 vector is 1, 0. So when we multiply these, we get 1/2 times the vector 1, negative rad 2, and 1. And so when we bring this 1/2 in, we get 1/2 negative rad 2 over 2 and 1/2. Okay, now again, this vector should automatically be a unit vector. It doesn't hurt to check, but if we've done things correctly, it should be a unit vector. And we can figure out our U2 vector in the same way. So again, this is 1/2 times this matrix above. Times our V2 vector, which is 0, 1. And we can multiply the 1/2 in again. And we get this as our U2 vector, okay? So again, it should be a unit vector automatically, and if we check the two vectors we found here, they should be orthogonal to each other, okay? But now we've run into a bit of a problem, okay? Because if we remember this, we want our matrix, we want our U matrix, I'll use a nice bright red here. So U will be, or is supposed to be, a 3 by 3 matrix, okay? Now, we've got 2 columns for the matrix U, but we don't have a third column. And if we hope to use this formula here to find a third column, well, we're going to run out of luck because we've run out of vectors V to plug into the formula. So we're at the point where we've used this formula here all we can. We've used it and gotten as many vectors as we're going to be able to get out of this. Now we have to just find a third vector that's orthogonal to the 2 vectors we already have. Okay, so this is where we have to kind of resort to some techniques and some tricks we've seen before. But ultimately, we just need to find a third vector that's orthogonal to U1 and orthogonal to U2. All right, so let's just make a note of what we need here. So we need to find a vector U3 which is orthogonal to the 2 vectors we already have. Okay, and this is in order. Okay, and this is in order to fill up, so that we have enough vectors to fill up the matrix U, which is supposed to be 3 by 3. Okay, so let's say the vector we're looking for, let's say that U3 is equal to X, Y, and Z. Okay, so it's some vector we're looking for. We don't know what it is yet, but we want it to be, we want the dot product of U3 and U1, we want this dot product to be 0. So our vector is X, Y, Z. Our U1 vector is 1/2 negative rad 2 over 2, and then 1/2. So when we take this dot product, we get 1/2 x minus rad 2 over 2y plus 1/2 z equals 0. So this equation here has to hold. Okay, in order for u3 to be orthogonal to u1, we want this dot product here to be equal to 0. Okay, so that gives us our first equation. We also want u3 to be orthogonal to u2. So that's going to give us another equation. So we want x, y, z dot negative 1/2 negative rad 2 over 2 and negative 1/2. We want this dot product to be equal to 0, and that's minus 1/2 x minus rad 2 over 2y and minus 1/2 z. So that's supposed to be equal to 0. So if we want both of these vectors, if we want u3 to be orthogonal to both u1 and u2, we really want this equation to hold and this equation to hold. But that's just a system of 2 equations and 3 variables, and we know how to solve that. So if we write down those 2 equations as an augmented matrix, we can just row reduce to find the solution. Okay, so I take these 2 equations here, I translate them into an augmented matrix. If I row reduce this matrix, I am going to get 1, 0, 1, 0, and 0, 1, 0, 0. Okay, so therefore x is equal to minus z, and y is equal to 0, where z is our free variable. So we take x, y, z. We're going to replace x with minus z. We're going to replace y with 0 and leave z as our free variable. And that's, again, just we pulled those substitutions from here. And when we pull z out, we get negative 1, 0, 1. Now, I want this to be a unit vector, so I'm going to pick z to be, say, 1 over rad 2. Let's say z equals 1 over rad 2. That's going to give me a third vector, which I'm going to call u3, which is negative 1 over rad 2, 0, 1 over rad 2. Okay. Now, at this point, it's always a good idea to just double check. So let's make sure that this is a unit vector. It's supposed to be a unit vector, and it is. The other thing we should check is that we tried to pick this vector so that it was orthogonal to both u1 and u2. And if we check, it is indeed orthogonal to both u1 and u2. So this is a good choice of a u vector. So once we have our third u vector, that's now enough to fill up the u matrix. And so let's take the 3 vectors we found and plug them in here, okay? And we're going to continue with our Prussian blue. Oops, yeah, 1 over rad 2. Okay, so this is an orthogonal matrix, or at least it should be, so you should check that. And now that we found our U matrix, we found our sigma matrix, we found our V matrix, what we ought to do is we ought to now check. We want to check that our original matrix, which was A, is indeed equal to U times sigma times V transpose. And we can take a look at the next slide, and that is indeed the case. This is our U matrix, this is our sigma, and this is our V transpose. And when we multiply them together, we do indeed get the A matrix here. So now that we've got a few examples under our belt, I think it's worthwhile stopping for a minute and just trying to make a few observations that might make our lives a little bit easier going forward. So let's look at the 2 examples we saw. So in example 1, the matrix A was a 2 by 3 matrix. Okay, so what we were doing is we were trying to find a singular value decomposition. And to do that, we were trying to split it up into U sigma V transpose, where U is a 2 by 2 matrix, sigma is a 2 by 3 matrix, the same as A, and V is a 3 by 3 matrix. So let's kind of think through the steps we had to do to find this. So first of all, to find the matrix sigma, we had to find the singular values of the matrix A. But to find the singular values, we needed to find the eigenvalues of the matrix A transpose A. Okay, so if A is a 2 by 3 matrix, okay, then A transpose is going to be a 3 by 2 matrix, and when we multiply them together, they're going to give me a 3 by 3 matrix. So ultimately, to find the matrix sigma, we had to find the singular values of A, which involved finding the eigenvalues of a 3 by 3 matrix. So that means we had to find the characteristic polynomial, we had to factor it, and we had to find the roots of that characteristic polynomial. Then, when we wanted to find the columns of the matrix V, we needed to find the eigenvectors of this 3 by 3 matrix. So you can kind of see that in this example, finding the singular values and finding the eigenvectors of A transpose A required a little bit more work because we were dealing with a 3 by 3 matrix, okay? On the other hand, once we found the singular values and we found these eigenvectors here, to find the matrix U, we just had to plug them into the formula Uj is equal to 1 over sigma j times AVJ. Okay, so there was a little bit more work on the front end because we were dealing with a 3 by 3 matrix and we had to find the eigenvalues and eigenvectors of this 3 by 3 matrix. But once we did that, finding the U matrix was pretty straightforward. We just plugged everything into this equation here. Okay, in the second example, example 2, in this case A was a 3 by 2 matrix, and so the U matrix we were looking for was 3 by 3. The sigma matrix we were looking for was a 3 by 2, and the V matrix we were looking for was a 2 by 2. Okay, so in this case we had to find the eigenvalues of A transpose A, which is a 3 by 2, so A is 3 by 2, A transpose is 2 by 3, and so when we multiply them together, we just get a 2 by 2 matrix. So in this example, we had to find the eigenvalues of A transpose A, but it was only a 2 by 2 matrix, so things worked out a lot easier. The characteristic polynomial was easier to find, it was easier to factor, and so on. Also, finding the eigenvectors was also easy, and it allowed us to build the V matrix pretty easily. Okay, so in this case, the beginning work involved a 2 by 2 matrix, and so we were able to find sigma and V pretty easily. Okay. On the other hand, when it came time to build the matrix U, now we're looking for a 3 by 3 matrix. And so we try and use this formula, and it works for the first couple vectors, but eventually we run out of vectors from the matrix V to use in this formula. And once we run out of those vectors, now it comes time to trying to find a third vector to use. And so we had to do a little bit more work on the back end to build the matrix U. So you can kind of see that in some cases, depending on the shape of the matrix, you might have to do more work on the front end or you might have to do more work on the back end. Now, if you liked either one of these problems more than the other, the good news is you can always kind of convert your matrix so that it's either easier to find sigma and V or easier to find the matrix U by just taking the transpose of the matrix. So why is this helpful? Well, we have the following useful fact. Suppose that we have a matrix A and we found a singular value decomposition of this matrix. So we split it up into a product U times sigma times V transpose. Well, if we take the transpose of both sides of this equation here, we get that A transpose is equal to V times sigma transpose times U transpose. Now, if we think of each of the matrices involved in this, V is going to be an orthogonal matrix, U is going to be an orthogonal matrix, and sigma transpose in the middle is going to be one of these fake diagonal matrices. In other words, these matrices here each satisfy the properties that they would need to in order for this product here to be a singular value decomposition. Okay, this factorization we've got here satisfies the definition of a singular value decomposition. Okay, but it's not a singular value decomposition of the original matrix, it's a singular value decomposition of A transpose. So if we step back for a second and think here, what this tells us is that if we want to find a singular value decomposition of a matrix, okay, what we can do is we can find a singular value decomposition of its transpose, and all we have to do is we have to take the matrix U and V and swap their positions. Okay, so we swap the roles of U and V, and we take the sigma matrix and we take its transpose. So if you know that a singular value decomposition of a matrix, you can pretty easily find a singular value decomposition of its transpose by just swapping U and V and taking the transpose of the sigma matrix. Now, why is this helpful? Well, suppose we gave you a matrix A that was like a 2x4 matrix. Well, in order to find a singular value decomposition of this, you would need to find the eigenvalues and eigenvectors of A transpose A, which is going to be a 4x4 matrix. Now, obviously, that's going to be a lot of work. Finding the characteristic polynomial of a 4x4 matrix is going to be pretty gnarly. But what you can do is if you instead look at A transpose, that's going to be a 4x2 matrix. And now, when you're looking at a singular value decomposition of this, what you're really doing, now all you'll really need is you'll need to find the eigenvalues and eigenvectors of a 2x2 matrix, which is going to make that initial step quite a bit easier. Okay? Now, so you could do that, you could find a singular value decomposition of A transpose, and then to get a singular value decomposition for the original matrix, what you'd have to do is you'd have to swap the roles of U and V, and you'd have to take the transpose of the sigma matrix. So in summary, sometimes it's easier to find a singular value decomposition of the transpose of a matrix, and then use that SVD to find an SVD of the original matrix. And all you have to do is swap the roles of U and V and take the transpose of sigma to do that. Okay, so give that a shot. You definitely don't ever have to do it that way, and most times I won't do it that way. I'll just kind of go straight forward with the matrix they give us, but you may find that it's useful in doing some homework questions or doing some exam questions. So there's a couple more theorems to talk about before we finish off this section. The first involves kind of a generalization of the spectral decomposition. Okay, now you'll remember from section 5.4, this is where we talked about it. Why am I not able to write? 5.4, if we have a matrix A that's square, so n by n, and symmetric, what we can do is we can take the matrix A and we can split it up into a bunch of pieces that look like this. Okay, lambda 1 times U1 transpose plus all the way up to lambda n UN transpose, okay? Where, of course, the lambdas are the eigenvalues of A, and the U1 up to UN, these are going to be the eigenvectors which have been normalized and which are orthogonal to each other. So they're orthonormal eigenvectors. Now, this theorem has a lot of applications. It's really, turns out to be quite useful that you're able to sort of take a matrix A and split it up into a bunch of rank 1 pieces. But ultimately, it ends up being somewhat restrictive that it only applies to n by n symmetric matrices. So there is sort of a grown-up version of this theorem that involves this singular value decomposition, which I'll go ahead and state now. So let A be an m by n matrix, and suppose these are the singular values here. So we've got sigma 1, sigma 2, all the way up to sigma r. Suppose these are the positive singular values, so these are the ones that are not equal to 0. These are all the ones that are bigger than 0. And then suppose that all of the singular values that come after sigma r, suppose these ones are all equal to 0. Okay? So this is kind of our setup. Now remember, the number of singular values that a matrix has, that the number of non-zero singular values tells us the rank of the matrix. So this setup is basically telling us that A is a rank R matrix. Now suppose that U1 through UR are the left singular vectors, and V1 through VR are the right singular vectors of A, which correspond to the non-zero singular values. So what this means is that U1 through UR, these are the first R columns of the matrix U, while V1 through VR are the first R columns of the matrix V. Again, we're not taking all of the columns of U or all of the columns of V, we're just taking the first R of them, where R is the number of non-zero singular values. Well, if this is our setup, then what we can do is we can take the matrix A and we can split it up into these pieces here. Okay, so sigma 1 times U1 V1 transpose, sigma 2 times U2 V2 transpose, and so on. Now it turns out that each of these matrices here is going to be a rank 1 matrix, the same shape as the matrix A. And so this gives us a way to take the matrix A and split, so the matrix A, which might be very complicated, and split it up into a bunch of simpler pieces which all have rank 1. So we call this the outer product form of the singular value decomposition of A. Ultimately, it really contains all the same information that this is a singular value decomposition up here in the top left. This contains all the same information that this does. Okay, these are just two different ways to sort of express the same thing. And so this theorem here has a lot of applications, and I outlined one of them with sort of that image compression example I showed you at the beginning of this section. So let's see an example. Let's find this outer product form of the singular value decomposition of this matrix. Now you may remember, I'm going to use a nice phthalo green here. You may remember that this is the matrix from the first example. All right, so we've already found the singular values. We've already found the left singular vectors and the right singular vector. So let's just kind of write them down to refresh ourselves. So we know that sigma 1 is equal to rad 3, sigma 2 is equal to 1, and sigma 3 is equal to 0. So looking at these values here, since I have two singular values that are non-zero, this tells me that the rank of my matrix is equal to 2, and that's going to be the R value that we see in the theorem back there. Okay, so in other words, the matrix A can be split up into sigma 1 times U1 V1 transpose plus sigma 2 times U2 V2 transpose. Okay, now of course we could write plus sigma 3 U3 V3 transpose, but because sigma 3 is just equal to 0, because everything after this point just has a 0 singular value, any terms that come after it are just going to be 0. So we don't even really bother to write it down because it's just going to give us 0 contribution to the whole matrix. So let's write out what these values are. So sigma 1 is rad 3, U1 is 1 over rad 2, 1 over rad 2. V1 was 2 over rad 6, 1 over rad 6, 1 over rad 6. I probably don't even need to remind you. I'm sure you all remember this example very well. And then our sigma 2 value is a 1. Our U2 value is negative 1 over rad 2, 1 over rad 2. And then my V2 is 0, negative 1 over rad 2, and 1 over rad 2. Okay, so when I multiply these vectors in these matrices, I'm going to keep the rad 3 on the outside. This is going to give me so I'm going to get 1 over rad 3, 1 over 2 rad 3. I'm going to draw this a little bit more carefully. So 1 over 2 rad 3 and 1 over 2 rad 3. Really testing myself in the simplifying fractions with radicals in them department here. This is going to be 1 over rad 3 down here, and then 1 over 2 rad 3 and 1 over 2 rad 3. Okay, so this is a rank 1 matrix. It's kind of a simple matrix because it's just both rows are the same. And then plus 1 times this matrix here is going to be 0, 1/2, minus 1/2, and 0, minus 1/2, 1/2. Okay, And so we see that each of these matrices here has rank 1. Okay, and somehow these two matrices, when you add them together, you add these two simple matrices together, they give you the original matrix A. So this is exactly what we did with that very first example I showed you with that picture of my daughter at the beginning of the part 1 of this section here, right? So there we had a picture. Maybe I'll it was represented as a matrix. I'm going to call it P for picture. Okay, and it was I believe I remember the rank was something like 1981. Okay, so it had 1981 was the rank of this matrix. So what that means is, using a singular value decomposition, we can split it up into terms that look like this. All the way to sigma 1981 times U 1981 times V 1981 transpose, okay? So we could take that complicated image that was made up out of all these pixel values that were, that formed this image of my daughter, and we could split it up into a bunch of really simple rank 1 pieces, okay? Now, to get a lower rank representation, to compress the image, what we did is we just decided that at some point these singular values weren't really big enough to really contribute to the overall image all that much. So what we did is we basically threw away the terms after some point in this decomposition, and we just kept sort of the first n term, or the first k terms. And if we go back to the beginning, I think it turned out that if we took sort of the first 80 terms, it ended up giving us an image that was almost indistinguishable from the original image. Okay, so really, this sort of has really immediate applications to things like image compression, but also a lot of applications to other fields, especially in things like data science and stuff like that. So just a couple more theorems to talk about here. This theorem here, I'm going to skip it. I'm not going to say that I don't understand it. I understand everything, but this is like the theorem where if you were to bump into me over the summer, say in July or something, and you asked me about this theorem, I wouldn't really remember what it says. It's the kind of theorem that I have to remind myself every time I talk about it. So it's not really a crucial theorem. It just basically tells you that if you look at the vectors, if you look at the columns of the U matrix and the columns of the V matrix, it turns out that by sort of the first R columns give you an orthonormal basis of the column space, where if you look at sort of the R plus 1 through mth column, you get a basis for null A transpose. So yeah, I don't know if this is going to be crucial knowledge for you to kind of hang on to, so I won't spend much time here. But for those of you who are looking for something to do over the summer and just want to kind of keep your linear algebra fresh, this is a good theorem to kind of come back to and just remind yourself of a lot of the fun things we've talked about so far. The last theorem is important, and it's again the invertible matrix theorem. We've seen the invertible matrix theorem come up time and time again in this class. So remember what this theorem is telling you is that if I give you a square matrix, an n by n matrix, then there are a bunch of facts that are all equivalent to that are all equivalent to the matrix being invertible. So here's a lot of the things we saw. So for example, if A is an n by n matrix, then saying that A is invertible is the same thing as saying that the rank of the matrix is equal to n, or that the nullity, in other words, the dimension of the null space, is equal to 0. That's equivalent to the determinant being non-zero, which is equivalent to saying that the columns of the matrix are linearly independent, or so on, right? So there's a lot of facts that really kind of, when you're talking about square matrices, there's a lot of facts we've seen that are enough to tell you that the matrix is invertible. So there's a lot of sort of different ways to test whether a matrix is invertible if it's a square matrix. But we have some new ones to add to this list. So we saw that if 0 is not an eigenvalue of a matrix, then it means that matrix will be invertible. So if you know the eigenvalues of a matrix and you know that 0 is not one of them, then you know that matrix has to be invertible. It turns out that if 0 is not a singular value of that matrix, then that also is enough for you to conclude that the matrix is going to be invertible. So if your matrix is n by n, so why is this true? Well, if your matrix is n by n, then that means you're going to get n singular values. Okay. Now, if all of them are non-zero, right? If 0 is not one of these singular values, then what that means is it means that these are all non-zero. Okay? Now remember, the number of non-zero singular values tells you the rank of the matrix. So if all of these are non-zero, it means the rank of your matrix is equal to n. And remember, that's equivalent to saying that the matrix is invertible. Okay? So knowing that 0 is not an eigenvalue and knowing that 0 is not a singular value, both of those are enough to tell you that your matrix has to be invertible. Again, in the case of a square matrix. So there's a few other things we can add. If the row space of the matrix is all of Rn, then that means that the rows span Rn, which means that it is an invertible matrix. You can say something similar about the column space. If you remember that the orthogonal complement of the row space is equal to the null space, then orthogonal complement of the row space is equal to null A. And if null A is equal to the 0 vector, then that means your matrix is invertible. You can say something similar about the column space. You can say something about the null space, orthogonal complement, yada, yada, yada. We have a lot of different conditions here. So the bottom line is there's lots of ways to look at a square matrix and to determine whether it's going to be invertible or not. All of the conditions on this list are enough to tell you that a square matrix is invertible. Now, I wouldn't go through, I've said this a bunch of times, I wouldn't go through and memorize each of these facts, but it's good to be able to sort of jump from one to the other and sort of understand why one fact sort of is equivalent to the other fact holding true. And so if you can kind of do that, if you can kind of jump around the invertible matrix theorem, and you can sort of see why one fact implies another fact, which implies another fact, and so on, then you have a pretty good understanding of things that are going on here. And with that about does it for section 7.4, and also for any new material that we'll be covering in this class. I want to thank you for letting me into your home each night to share the magic and excitement of linear algebra with you. This is always a bittersweet time for me, watching my little eigenvectors leave the nest. But while this does it for the formal part of Math 213, remember that the joy and wonder of linear algebra live on with you. And while I won't be able to be there to continue with you on this journey, anytime you need to diagonalize a matrix or perform Gram-Schmidt, I won't be far away. Keep on row reducing.